Okay, let's start the seminar. Today's speaker is Polina Baron, who will speak about independent sets of matroids and log-concavity of accused polynomials. Please, Polina.
Hello, everyone. Thank you for coming to my talk. And today we are going to discuss independent set of matroids. And I suggest that we start with the basic stuff, with the definition of what a matroid is, which I'm assuming not everyone knows. We consider, I'm sorry, so something is, there's a sound that's quite often like chimneys, like bells.
В чем проблема, Полина?
Непонятный звук, как колокольчики.
Вот эти пилим, оповещения.
Это входят другие участники, не обращайте внимания.
Хорошо, спасибо. Right, so we'll start with considering a finite set. We will call it E. And the set can be just a set of numbers. For example, we can consider a set of numbers 1, 2, 3 or something. Or alternatively, we can consider a set of vertices of a graph. Say a graph like that. That's not a very interesting graph. We will use this example later. And actually, the matroids are very useful tool to study graphs, and we will come back to that later. So what is a matroid? A matroid is a...
Polina, sorry.
Yeah?
Usually the set of vertices or the set of edges. Normally.
There are two dual definitions. And I believe that actually, for our talk, you're right, for our talk, it probably will be easier to use the definition of the set of edges and not just use the dual definition at all. So for the duration of this talk, we will consider not the set of vertices, but the set of edges. Thank you for the correction. Right, so the matroid is a non-empty collection B, or rather just we can consider this whole, the matroid, the collection itself, of subsets of E. Those subsets we will call the bases, and the subsets satisfy the following exchange property. If we have two bases of the matroid, which I remind you are a subset of E, and there is and we pick just some random element of E, which belongs to B1 and does not belong to B2, there always exists an element E2 which belongs to B2 but not to B1. Sorry, I'm having some technical issues, sorry, but not to B1, such that the following set, E1 with E1 excluded and E2 added, is also part of our matroid. So that means that the definition of a matroid is fairly symmetrical. Like if I want to build a matroid out of this set, and say I include set 1, 2, and a set 2, 3, then I will have to include the set 1, 3, according to this rule. And
Полина, напишите, пожалуйста, что МАТЕ это подмножество в 2 в степени Е. У вас МАТЕ написано уже?
Oh, yeah, right. That's logical. So when it comes to graphs, the usual way of defining matroids, if we consider the set E, the set of edges, let me give them numbers, is through the trees on the graph. So the usual definition of a matroid of a graph is some subset of trees that span the graph. So for example, here I can consider trees. I can consider this tree, and I say I can consider this tree, which will also make me consider this tree, and so on. And the reason why we like to study the matroids is the following. If we consider a chromatic polynomial of a graph, and we consider the matroid that is related to this graph, then, if I'm mistaken here, right, then there is a following formula. Where mg is a matroid that we derive from the graph. This is the chromatic polynomial of a matroid, and C is just the number of connected components of the graph. As such, it's quite a useful instrument. And we will actually come back to the issue of chromatic polynomials later, if the time permits. But for now, I want to discuss a little different thing. So I will have to define. Sorry, won't happen again. Right, so now we define the matroid, and I want also to everyone to keep in mind a definition of an independent subset, which is a very important one. So an independent subset S is a subset of a matroid so independent subsets, in other words, are those that belongs to the matroids. It's actually kind of important that we understand that an independent subset is a subset of E, because later on we will have to discuss the subsets of sets, the subsets of the matroid, which is this the subsets of sets which belongs to the matroid. So it's kind of confusing, and I will highlight every time we encounter a subset which is not a subset of E but a subset of M. I will highlight that. And of course, if we are not talking about an independent set, then we're going to talk about a dependent set. And there is a conjecture made by Mason in 1970, which contains 3 statements of increasing strength. So by EKM, we define, we denote the number of K element dependent subsets.
I interrupt you.
Yeah.
Я не очень понимаю определение матроида вот в этом контексте. Если вы говорите, что независимое подмножество это элементы матроида, да?
Нет, давайте я по-русски скажу, потому что, видимо, сама запуталась. Есть изначальное множество Е. Есть матроид М.
Да.
и я поставила неправильный значок. И мы рассматриваем подмножество, множество подмножеств Е, которые... То есть мы в дальнейшем будем рассматривать как элементы матроида подмножество Е, а когда мы будем говорить слово подмножество элементов, мы будем иметь в виду подмножество элементов матроида, то есть подмножество подмножеств Е.
Ну, хорошо, ладно.
Maybe I should repeat that again in English because I think I created quite a confusion. So we have a finite subset E, which can be just perceived as a finite subset of n numbers. And then we consider a matroid, which is a subset of the set of all subsets of E. So it contains as elements subsets of E. And then we consider an element of the matroid. So we consider a set of some subsets of E, which belongs to the matroid. Yeah, I think I've created quite a confusion here. I apologize. So there are statements of increasing strength, which Mason suggested. So the first one is as follows, and I think I should write that E IKM is the number K elements independent subsets of an n element matroid n, where n is the number of elements of E. So then he improved this, then Mason improved and suggested the following. Then he improved it once again and suggested this.
Не знаю.
Независимо, это же странно, необычное определение.
Полин,
Yeah.
this looks strange because if we have a fixed set, a given set, M of E, yeah, then the number of subsets of given consisting of a given number of elements depends only on the number of elements in M of E.
It is C sub K and something like this.
Если у вас есть какое-то фиксированное множество, и вы рассматриваете подмножество в нем данной мощности, то это число подмножества определяется исключительно количеством элементов в исходном множестве. Правда ведь? Я бы все-таки считал, что значит, матроид – это набор независимых множеств, да, в данном конечном множестве. Если мы берем независимое множество с максимальным числом элементов, это элементы базиса, то они, во-первых, все имеют одинаковое количество элементов, им соответствуют остовные деревья, не просто деревья в графе, а остовные деревья в графе.
Yeah, that's correct.
То вот для них
Не просто леса, потому что другие, они будут лесами, правильно? Там они не связаны.
Ну, остовные леса, если граф не связан, то если граф связан, то остовные деревья, если граф не связан, то остовные леса. И вот эта аксиома обмена должна выполняться только для базисных B1, B2 это не просто элементы матроида, это базисные.
Yeah.
Вот тогда ЕК-ТМ это количество независимых подмножеств в В. И это подмножество не В мат Е,
Множество элементов.
независимое подмножество это подмножество в Е. Подмножество в Е называется подмножество в Е независимое, если оно принадлежит матроиду. То есть знак у вас правильный стоял принадлежности раньше.
Ну тут M
Just
это
confused
базис.
myself.
M это базис.
Ну, это зависит в разных местах. Да, вот так.
Тут, видимо, M это базис, там любых базис B2 и Z.
Там я бы поставил, что B1 и B2 это базисные элементы. Да. То есть элементы максимальной мощности. B это вот тогда будет понятно.
И там вот третья строчка, самый правый.
И в конце там тоже, в конце этой строчки тоже элемент должен принадлежать базису. Ага.
Ну, там нужно понять, если по ходу остального доклада там имелось в виду под M всегда базисы, то...
Ну, это...
Сейчас, что такое ИКА? Количество тканей.
ИК-ТМ это количество элементов независимых подмножеств. То есть количество элементов матроида, ну, скажем, количество весов, количество весов с корешками. Well, and who were the authors of this conjecture? There are 3 conjectures, yeah?
Yeah, there are 3 conjectures of increasing strength. And the interesting thing about them is that 2 of them were proved in 2018, one by quadriprocedure Katz, I hope I'm pronouncing the names correctly, and another by Schroeder. And
Can you write the names down?
Yeah, that would be a good idea. Right, so
if you have a graph, then the subset of edges of the graph is said to be independent, provided it contains no cycles. Yeah? Slow cuts. It's 1, yeah. 2, 3.
And what they did, they used combinatorial Hodge theory. Which actually made for quite complicated and technical proofs. What we're going to discuss here is the 3rd conjecture, one that is the strongest. And the interesting thing about it is that it doesn't really exploit the results of those 2 papers, and actually can be proved in, I'd say, a little easier manner, which is not usually what you encounter. And
are we going to discuss the conjecture number 3?
Can you please speak up?
Вот третью гипотезу будем обсуждать.
Yeah. So we are going to prove 3. We're going to prove 3, and then we're going to discuss how it's related to the Q-plots model and what results we can obtain from this number 3 conjecture.
Great.
So just a quick note. I believe that I do not have to define the rank function, but if I do, please just tell me and I will do it. I don't think it will take much time.
Define it, please. It will be convenient.
Right, so if we have a subset, let's call it A, of elements of the set of all subsets of E, we define the rank of E, the rank of A, given the matroid M, as the maximum size of an independent subset of A, which is kind of a mouthful. I wonder if I need to show, if I can show. Yeah, I think I can. Here, we can have both definitions. So I think that we have decided that I was wrong to change that sign, right? So we have some set of subsets of E, and we consider a maximum subset of this set that is an independent subset in our matroid. Eyes of it is the rank of A. So the rank is a function that maps all possible subsets to Z, or at least non-negative numbers. Well, technically, we can have series of non-negative numbers. And we also have to define another thing, which is a multivariate polynomial. And we define it in the following way, which I will relate to our matroids in a moment. So we consider K being a positive number, positive integer, and we consider Q being a positive number. Then we formally define a following homogeneous polynomial And then the homogeneous.
And A runs over the subsets in E.
Yeah, A runs over all k-element subsets of E. So we want to define the homogeneous multivariate.
То есть, мы же решили, что максимальное различное множество, подмножество. Что все-таки такое равно m2?
Это мы берем множество, мы берем любое подмножество в нашем круге и смотрим максимально независимое подмножество. Нет, это мы не пишем. Независимо от неуважения.
Во всем.
Полина, я только не вижу К в этом определении. К участвует.
It's hidden. It's hidden because A, we can actually, I think we can do that. We can say AK, and AK are AK runs through all k-element subsets of E. So k element.
Там А пробегает под множество К элементов. Множество двух. Е. Понятно, да. Тогда там показатель должен быть ранг m от АК.
Yeah. And I want to note that if we set if we set W0 to be equal to 1, then we will just receive the partition function of the Q-state Potts model, which we're not interested in.
Sorry, one more question. Do we suppose that n is the number of elements in E?
Yeah. Right.
Now it's clear, yeah.
Right, we will come back to the Q-state Potts model later. I think that I don't have to define it, given that I did it last quarter.
What is W0?
The новый переменный.
Right, so now we will come back to proving our.
Sorry, once again, will you return this to the previous line?
Yeah, sure. How far back?
When you are writing I belongs to AK, do you mean WI? Yeah.
WI is the weights of edges.
No, it's not a weight, it's just a number.
No,
It's a
yeah.
number of zeros. Okay, yeah.
And why is that?
It was satisfied some deletion
Yeah.
contraction. Was satisfied certain deletion contraction relation. Yeah.
So you state that it is a type polynomial, yeah?
That's the definition. There is no statement. So it's a definition.
So then,
Okay, sorry for interrupting.
Shall I continue? All right. So we will come back to proving the relation that we love so much. And then after we prove it, I will explain why it's nice and why we want to use it for the POTS model. For the time being, as I said, if we assume that W0 is just 1, we will actually obtain the position function of the Q-state POTS model. And that's a small to how we will suddenly change the setting we're in and go to POTS model. So the way we're going to prove our theorem is through a heavy use of the Hessian matrix, which is which I'm sure everyone here knows, but just for the sake of clarity, I will write it down. So we have a homogeneous polynomial, then we of course can write its Hessian. Which will be an n+1 by n+1 matrix, which I note that it has a simple and positive eigenvalue just by the Baron-Benioff theorem.
It is positively definite, yeah?
No. I've said that we have a Baron-Benioff theorem to tell us that it has one positive eigenvalue. We don't have anything, we don't know anything about other eigenvalues. But one positive eigenvalue we should have.
Yes, there is a positive eigenvalue of this matrix, yeah?
Yeah, a positive eigenvalue. We don't know if this eigenvalue is the only positive one, or if there are some other positive eigenvalues. In fact, what we want to prove, and what will give us the desired result, is that the Hessian has only one positive eigenvalue. Well, of course, we technically should say that it has only one positive eigenvalue for any W we can throw at it, and for some bounded Q from 0 to 1, because eigenvalue of a Hessian without defining the point, it's not much, doesn't make much sense to talk about it.
Who is Q small here?
If you can, if you recall, the way we define two polynomial required us to use some sort of a dummy variable Q, which is a parameter, which is used here, and then of course hidden here.
And to whom does this theorem belong?
This theorem belongs to, hold on, it belongs to Peter Brandon and Jun Ho.
Jun Ho.
Let me write it down.
Yeah.
So the names of people responsible are Brandon. Right, so we are going to prove this theorem in a little bit convoluted way, because what we're going to do is we will use the notion of log-concavity to prove a little stronger result, and then this strong result will prove by induction. So I will hope that we will not lose the connection with the first theorem, but if you do, just ask me, I will tell you how that's all connected. So do I have to define strictly long concave sequences?
Yeah, please recall it.
Yeah. So suppose we have a sequence of n+1 numbers, like this one, and it belongs to the following code. So all of them are actually positive. We're not allowed to have negative numbers and not allowed to have zeros. So we say that C is strictly log concave if for any m from 1 to n-1, the following holds. Which one may note the strong resemblance to what we've seen when we discussed the initial formula we now are trying to prove in a very convoluted way. That's not a coincidence. So for right now, we'll start working with a little bit refined definition of 2 points. Namely, we will apply the strictly long concave sequences with polynomials, and we will write an almost the same formula, but with the strictly long concave sequence as a weight. And one could see that we can consider the initial sequence as a sequence with C equal to just 1, 1, 1, 1, 1, 1, 1. And as such, the 1, 1, 1 is not a strictly long concave sequence, but it can be perceived as a limit of strictly long concave sequences. So if we prove something for strictly long concave sequences, we can just take the limit and go back to our initial case.
Значит, идея состоит в том, чтобы рассмотреть, чтобы доказать это утверждение для последовательности строго логарифмически выпуклой, да, для любой, а потом единицы рассматривать как предел последовательности строго логарифмических выпуклой. А мы будем как-то выбирать специальным образом эти строго логарифмически выпуклые последовательности или для любой?
Well, not really, no. I suppose that, I don't think that there are any conditions, actually. We sort of want to do it because then we can facilitate our work with the Q-POTS model, I guess. And because some statements are much easier to prove in this setting. So the actual theorem that I will prove in earnest is the following. We consider not just the Hessian, but the derivatives of Hessians, which are just we have numeration from 0. Assuming that this is not identically 0, there are two statements for that polynomial that hold. And one is that the Hessian
Нам нужна последовательность, когда в коэффициентах точности единицы.
Да.
Ну, так, это реально, значит, но точность единицы не строго будет последовательность, потому что
Она просто
каждое элемент произведения будет соседей. Но мы, если мы получаем ее как предел последовательности,
а там у нас конечная сумма.
These are assumptions or assertions of the theorem.
No, those are assertions.
Assertions, yeah.
Those are what we want to prove.
Well,
Right. And actually theorem 1 is the case of just considering the statement 2 of the theorem 2 and
so,
keep equal to 0.
M in the second assertion is the Hessian.
I'm sorry, it's it.
It is.
It has, yeah. It's just it. So let's look it up. So I want to tell you a technical lemma, and I sort of don't really want to prove it because it's basically linear algebra. And the lemma is the following. We consider a symmetric matrix which of course stands for our Hessian. And we suppose it has a positive eigenvalue. Not necessarily one. So these statements will be identical. Maybe we'll just write the statements again.
You mean equivalent, yeah?
Sorry?
You mean that these two statements will be equivalent?
Oh, yeah, sorry. So A has one eigenvalue that is positive and only one. For any U, W, into Rn plus 1, such that this holds, we can write the following. And very similar, there is a vector U belonging to Rn plus 1, for which this property holds, such that for any W belonging to N plus 1, we have the same inequality. I suppose that we don't really have.
Why can't we divide those sides by the same element?
Sorry. Yeah, because that's W. That should have been B. Sorry.
Yeah, it should be.
Oops.
I'm sorry, I didn't do anything. I'll have it back in a moment. Can you see it yet?
Not yet.
Now?
Now it's much better. And we see everything. Great. And I think we can believe in the assertion of this lemma.
Yeah. So basically, that's just heavily applying Cauchy interlacing theorem. And now we divide. Now we will divide basically.
Ну, это специфическая ситуация, когда можно положить собственное число.
Now we'll divide basically the assertion of our theorem 2 into two lemmas. First one will be the base of the induction, and the second one will be the induction itself. So first, I suppose I can call it lemma 4. I want to induct by the degree of this polynomial. And first I want to prove that in case of degree 2, the assertion of the theorem holds.
But if the degree is 2, then the Hessian is just a constant, yeah?
But I think
this is a constant.
Not necessarily true. I think that in this case, no, yeah, you're right. It is a constant. It is a constant, but it doesn't quite help us because we want to prove that we have only one positive eigenvalue.
Yeah, sure.
And I don't see an immediate corollary here. We still have to work on this constant. Maybe there is an immediate corollary, but I'm not seeing it. So we can actually if the degree is 2, we're actually only interested in the case we can have something like that. Whereas is a K element. Subset E. Because if we have di with I bigger than 1, will be or equal than 1. equal to 2 or bigger, then we'll just have, well, at best we'll have a constant. Worst we have a 0.
Я правильно понимаю, что теорема 2 доказывается по индукции. Сначала мы доказываем для самых глубоких производных, а потом постепенно, потом делаем шаг индукции, переходя от производных какого-то порядка к производным порядка на единицу меньше.
На единицу больше.
На единицу больше это так убьем еще члена, нет? Мы же хотим вернуться к самому, к исходной функции.
Нет, подождите, индукция идет не по альфа.
Не по альфа, да? Теорема 2 говорит, что Бесян
имеет положительное...
Нет, индукция идет по степени многочленной идет индукция.
Ну, может, да, так или иначе.
Это не совсем, ну, то есть это не совсем то, что первое приходит в голову, но делать индукцию по...
Нет, я понимаю.
Было бы неудобно, потому что на самом деле это не одно число, это много чисел.
Угу.
Поэтому мы доказываем для двойки, дальше мы доказываем шаг индукции, и дальше мы, наконец, получаем, что мы хотим.
Okay.
Right. So we can basically just... We're going to basically just do some computations. I want you to be mentally prepared for that. We have here, I want you to recall that this, I maybe should write it down again, right? So this is equal to the following. Right, we decided that we want to write AK, actually AL in this case. This is a contraction. No, this is a contraction of M by I. And did I define everything? Oh no, this is me forgetting to write letter K. Now we did. Then you can consider.
Только лучше J, наверное, использовать в качестве воспроизводной.
Yeah, that should be better. Then we can consider the following kind of important quadratic form.
Значит, когда мы стягиваем итое ребро, это более или менее то же самое, что многочлен так от графа со стянутым ребром, это все равно, что производная. Многочлен так от нестянутого, исходного многочленного такта по переменной, отвечающей стянутому ребру. Вот что здесь написано. А вторая производная берется по каким переменным?
What do you mean by the second derivative?
Okay.
That's just alpha.
That's how. I see.
Yeah, maybe do better. Right, plus. What a crocodile. Right, and just to make sure. Right, so S is a k-element subset, the one we sort of fixed at the beginning of the proof. And this is the contraction. And everything else are basically just formulas that we've already seen. So we want to prove that the Hessian, this monstrosity, because this doesn't matter, it just basically makes the formula nicer. This thing, we consider it just a constant. So we want to prove that this monstrosity is non-singular and has exactly one positive eigenvalue. I want to note that by contraction, we will at some point arrive to the situation where S is equal to an empty set and K is equal to 0, which is where we will stop because nothing more to contract. So in this case, we will be able to write this quadratic form in the following manner. Where A is just 1/2 of a Hessian. That's just basic linear algebra. And now we have precisely the setting of the lemma 3. So to prove that this quadratic form has just one positive eigenvalue, we can prove either the second or the third equivalent statement of lemma 3. And it would be easier to prove the third equivalent statement because we just need to find one vector. And we can just show that it exists by explicitly constructing it. And in fact, the vector that we want could not be simpler than the following. So I remind you that what we want to prove is that the following holds for
So you mean that this vector is an eigenvector with a positive eigenvalue?
Yeah. Yeah. We know that we have one positive eigenvalue, and we can just consider ourselves being in an orthonormal basis of eigenvalues. So why not take the vector that corresponds to this one positive eigenvalue? Can go much simpler than that. So we can definitely consider the vector v not to be the multiple of the vector, and not to be a multiple of a vector, of the vector u, because this whole thing just reduces to equality if that's a multiple. So from this horrible crocodile, what we want to prove, didn't mean to do that, reduces to much nicer formula. Whereby T we will denote the following constant, just to not carry it with us all the time. Is to be proved for any W belonging to R and so on. And the reason this really is so simple is that substitute.
In the definition of T, is it indeed over C1 or over C1 squared?
Yeah, C1 squared. And the reason it's suddenly so easy is that we've used the vector u, which is 0 everywhere except for the first coordinate. And so that's how we gotten rid of most of the terms in this spread equation. So now we are going to introduce more definitions. And the definition introduce is the definition of a loop. And the loop is an set X, which is a subset of E, such that it is not contained in any independent set.
Should it be minimal, non-independent set or not?
Well, I think we can
Yeah, that's
situation when the minimal non-independent set is an empty set.
All other, if we have other subset containing X, it's of course not independent because otherwise it's contradiction.
Нет, значит, петля это такой элемент. Лучше просто написать, что X как элемент такой, что который не входит ни в какое независимое пространство.
Если он сам является независимым,
Нет, но сам он тоже не является независимым.
Да, если он сам не является независимым, то он не может ни в какой независимый входить.
Да. Okay.
And moreover, we want to define the parallel classes. We say, let's say that all elements of E such that this holds denoted by E0. And we can have we can actually have the elements sort of, what's the English word? Split into parallel classes. So let's say S1 belonging to M. And we say that S1 is parallel to S2 if the following set is dependent. So not independent.
Ну, то есть это два ребра, соединяющие одну и ту же пару вершин в графе. Они параллельны, если они соединяют в графе одну и ту же пару вершин, тогда вместе они образуют цикл. Значит, они являются зависимым множеством. Нет, два ребра.
I haven't heard the last one.
Я говорю, что два ребра в графе зависимы, если они соединяют одну и ту же пару вершин. Но они параллельны тогда, да. Правда?
I'm trying to think that in terms of graphs. The problem is that the graph definition was from another paper. This paper just used the set definition, so it's not absolutely immediate for me.
Okay.
I think that it's not that it is. It's not what it is. But I probably shall carry on and then discuss the graphs if I have time. So we want to do a change of variables. If we have G that is not a loop, we distinguish it by sending WG to QWG. And then let us denote by E, which letters have unused? EM, U. Degree, M, elementary symmetric polynomial. In variables, with G, where G belongs to U. So this change of variables sends us to an even nicer place. So this change of variables give us the following. We can actually write this polynomial as 2e minus 1 minus q e 2e1 plus should be e0 or not. No, that should not be e0 because this change of variables, yeah, it shouldn't be e0. Sorry. So we have this nice formula, which we will use to prove the statement that I actually think I want to to say that this is the statement star and refer to it like that in the following. We want to prove statement star. And actually, we can sort of simplify our work because we're working with log-concave sequences, which means that we have the following.
Где больше это есть, которые говорили.
And then it suffices to prove that if right, and I forgot to say that in case Z1, this formula will become very, very simple. So simple that I even forgot to mention it. Just be like that. So note that if Q is equal to 1, then what we want to obtain is just the Cauchy-Schwarz inequality. But unfortunately for us, Q is not necessarily equal to 1. So we are still fighting, but we can sort of choose our fights and note that since this is the thing we want to prove, I'm hoping you see my cursor, then actually we can go in further and reduce to the following. And it's even nicer because it's even nicer because we have maybe I should write it as a theorem. So if this is less than 0, then this will be bigger than 0. So that's the only case we will consider from now on. Because otherwise it's from an atonicity, we will have this result still. And moreover, we have this formula monotonous in Q. So we can also consider the case Q equals 0 because it's the worst. So those two are the worst two cases that can happen. Anything else will be better. We can go much worse than what I currently wrote. So then we actually did great work to reduce our horrible, horrible formulas to the following. And that actually just follows from the Cauchy inequality.
Polina, if you are out of time,
Yeah.
can you just name the state of...
Yeah, it takes much longer. Well,
ideas you
Actually, at this point, the proof of the lemma 4 is more or less concluded. So I suppose I can just state another few steps that will get to the proof of the theorem.
yeah.
So one of this, I will call it step 1, I guess. Is to prove that if we have f at degree d homogeneous polynomial, in W, where W is actually a tuple W0 to Wn, we can consider the Hessian of a derivative of f if for any e this thing has one positive eigenvalue, then we can prove the following. Right, we'll need that. And now I've promised you induction. The base was covered. Now we want to induct by the degree d of homogeneous polynomial, which is d alpha z m c.
Yeah.
So consider some f I do not hat of degree of degree m there is d plus 1. We can use this step 1 to note that the Hessian of any derivative of f will be non-singular and has exactly one positive eigenvalue. So theorem 2.1 is just a corollary of step 1. Moving on, this will be a little trickier. We can remember a trick. We can remember a trick with decomposing f into homogeneous symmetric polynomials. And supposing that q equal to 1, we can write f equals to minus 1. and so forth. This actually can be written for clarity of how we will continue, so forth like that.
But still, the sequence C is arbitrary, yeah?
Now we will want to sort of play with this sequence a little. So we are not forbidden to choose our sequence C such that CE equals 0, except for two E's. Then F is just the degree n plus 1 elementary symmetric polynomial. And then the Hessian which we will consider at the all ones vector. Will be equal to C multiplied by matrix Gn plus 1. Which is, how do I put it? Basically, it's C 0, 0, 0, 0, 1. So sort of an weird inverse of an identity matrix. And I will note that this C that we wrote is not a log-concave sequence, because we will have a lot of cases where we want to compare 0 with 0, they will be equal, and the strictly log-concave sequences demand inequality. But of course, this C that we chose can be approximated by a strictly log-concave positive sequence. And therefore, at some point in this limit, we will find a strictly log-concave positive sequence, C, I don't know, C bar, running off. With which this Hessian will be non-singular and have only one positive eigenvalue for Q equal to 1. We still consider the case Q equal to 1. But the eigenvalues are continuous in Q, and we've proved the first statement of the theorem 2, which is that the Hessian will be non-singular. So then, if we have the formula, the statement 2 of the theorem proved for one parameter, we can have it for all parameters Q from 0 to 1. And that basically how we prove theorem 2.
Okay, thanks. I believe we should stop here. Are there any questions to the speaker? There are no questions. Polina, will you close the screen? I'll try to add a few words. Just now, why we are interested in things about which Polina was talking. You know, if we have an arbitrary graph, and we take its chromatic polynomial, which is, let it be dependent on Q, and this will be some minus 1 to the power I ci Q to the power I. Then the sequence C1, C2, and so on proves to be log-concave. It is log-concave. Meaning that the graph of the logarithms of the elements of this sequence is concave. It's just concave. A similar statement seems to be valid for. Let me change. Would be it's by no means an easy theorem and rather recent, about 10 years ago, due to June 5th. Very interesting question seems to be whether the same is valid with the coefficients of the values of SL2 weight systems. Weight system. And put diagrams. For all the examples I tried to do that, it works. Indeed, you obtain a log-concave sequence of not necessarily integers. Саша, Женя Красильников got SL2 values of the SL2 weight system on graphs that are not. That do not have integer coefficients. But nevertheless, this property of log-concavity holds for these polynomials. And it would be very interesting to know whether this is always true. In particular, if this would mean that these polynomials are somehow related to certain unknown algebraic varieties. And the coefficients serve as certain cohomological characteristics of these varieties. That's because it's especially interesting. The part which Polina mentioned in the beginning. Okay, let's stop here. Polina, thanks a lot for a very clear talk. Are there any more questions or comments? If no, then let's have a break. Thank you.